Training a single major AI model requires gigawatts of continuous power and an immense land footprint. With developers maxing out traditional hubs, the search for abundant land and power has pushed the industry toward new frontiers, like northern Thailand. Geographically, the Chiang Mai corridor looks perfect: heavy industrial zones, major universities, and available real estate. But beneath the surface lies a trap. The city sits inside a deep basin filled with layers of soft, unconsolidated sediment. Analytically, Thailand is tectonically active. When a rupture occurs along the nearby Sagaing Fault, seismic waves travel through the dense bedrock cleanly. But the moment that energy hits the soft soil of the basin, it builds in amplitude, a phenomenon known as the jelly effect. Placing heavy infrastructure, buildings packed with multi-ton server racks and cooling tanks, on top of this amplifying geology invites severe soil liquefaction and catastrophic structural failure. To secure the physical integrity of a massive data center, the entire footprint must move out of the vulnerable basin and onto the stiffer, industrially hardened terrain of neighboring Lamphun. Escaping the seismic jelly effect solves the ground problem, but Lamphun shares the region's deadliest seasonal feature, the burning season. Between February and April, agricultural fires blanket the region in smoke, which gets physically trapped against the mountains. For humans, this dense particulate matter is a respiratory hazard. For high-performance electronics, it is a chemical threat. Wood smoke is dense with volatile organic compounds, reactive carbon-based chemicals that linger in the air. When these compounds mix with standard tropical humidity, they form acidic microparticles that settle on printed circuit boards, dissolving the microscopic copper and silver traces that connect the processors. Standard data centers rely on economizers, massive fans pulling in outside air to cool the hardware. Here, the acidic microparticles easily bypass standard filtration, rapidly clogging HEPA filters and causing widespread hardware failure within weeks. You cannot build a standard data center in Lamphun. Surviving this environment requires throwing out the legacy playbook and designing a facility around a 000 mandate: zero net carbon, zero water waste, and zero import reliance. The first mandate starts by abandoning air cooling entirely. Instead, the servers are fully submerged into baths of synthetic, electrically non-conductive dielectric fluid, a method called single-phase liquid immersion cooling. This fluid provides a perfect hermetic seal, completely isolating the sensitive electronics from the corrosive atmosphere. Because liquid conducts heat far more efficiently than air, it instantly absorbs the thermal load of the GPUs, eliminating the need for server fans altogether. Cooling the fluid requires power, but generating 20 megawatts of renewable energy via traditional solar farms would consume vast tracts of scarce agricultural land. Instead of clearing fields, the facility mounts bifacial solar canopies directly over the 18 kilometers of open concrete canals surrounding the local Quang River. This canal top array triggers a chain reaction of thermodynamic benefits. The flowing water naturally cools the underside of the solar panels, boosting their electrical output. In return, the panels shade the water, preventing algae growth from fouling the cooling systems and saving millions of liters of water from evaporating into the hot air. By combining immersion cooling with over-water solar, the facility secures its thermal survival while checking off the zero water waste mandate. But solar power has a blind spot. The sun sets, and data centers run 24/7. To establish reliable baseload power, the facility taps into the local industrial estate's waste streams. By placing concentrated industrial brine on one side of a membrane and treated wastewater on the other, they harvest blue energy. This is pressure-retarded osmosis. The chemical imbalance forces fresh water through the membrane, creating intense osmotic pressure that spins a turbine to generate electricity. Even with osmotic baseload power, the facility needs massive grid-scale batteries to buffer the solar array. Traditional lithium-ion batteries are prone to thermal fires in tropical climates, and they force a heavy reliance on imported minerals. To solve this, the facility switches chemistry. They use sodium-ion batteries, utilizing cathodes sourced directly from the billions of tons of natural rock salt sitting beneath Thailand's Korat Plateau. For the battery's anode, they bake local agricultural waste, like rice husks and coconut shells, to synthesize the necessary hard carbon structure: domestic rock salt, local crop waste, and osmotic pressure from wastewater. By sourcing its chemical requirements entirely from within its own borders, the facility secures its final mandate: zero import reliance. Legacy data centers operate as walled fortresses. They extract local power and water while offering few permanent jobs to the surrounding town. Project Salt Road flips this model, functioning as a symbiotic anchor for the community. The data center organizes a virtual power plant, a digital network that coordinates decentralized energy. They front the capital to install solar panels on the residential rooftops of the neighboring Lamphun villages. During the day, those rooftops generate excess power. Using an automated peer-to-peer trading mechanism, the data center purchases that surplus clean energy at a premium, zeroing out the residents' electricity bills while powering the servers. And when the severe monsoon season hits and the regional power grid completely drops offline, the arrangement reverses. The data center islands the local microgrid, isolating it from the national blackout. It then discharges its massive sodium-ion battery reserves outward, keeping the local schools, clinics, and homes fully powered through the storm. The ultimate resilience for digital infrastructure is its social license to operate. By designing systems that actively heal the environment and empower the communities they occupy, Project Salt Road establishes a global standard for a resilient, symbiotic, high-tech heartland.